anyone ever graphed a piecewise function? Have you heard of a piecewise function? Awesome. Okay, I might blow your mind a little bit today, but that's okay. We'll get through it. Okay, so let's get started. So we're going to do some graphing today. Before we do some actual graphing, let's just talk about some terms that we need to sort of freshen up on. What is domain and range? And when I ask you these questions, I throw out whatever you can at me. If it's wrong, we'll fix it. Hopefully we can all piece it together. You might hear someone say something, you'll be like, oh yeah, I remember. So give me whatever you have. What is domain and range? X and Y, okay. Which is X? Domain is X. All right, so domain is set of X values. And what is range? The set of Y values. And I don't really have any good way of remembering that except that D comes before R in the alphabet, X comes before Y, domain is X, range is Y. All right, what is a function? And that's a pretty big question, so we might actually want to start with this bottom question. Do you remember how we can tell if a graph is a function? Vertical line test. Okay, so let's start there. Okay, so we use that vertical line test. Let's say we use a vertical line test on a graph and we say, oh, that one's not a function. What do we base that on? Okay, so if we have a graph, let's say we have this sideways parabola. Okay, and I look at my vertical line and I see, oh dear, it's intersecting those 2 points. Okay, what does that tell me? That it is not a function. Okay, so we're kind of working backwards from this. So we use a vertical line test. That's how I would know from a vertical line test that something is not a function. So what is a function? What made this not a function? 2 values of X were the same, and they had different Y's. Okay, so what is a function? Okay, so she said a line, and let me say it could be a line, except a vertical line. That's definitely not a function, right? But every other line is. Okay, so it could be a graph of something such that what? Okay, that's how I would tell the vertical line test. But the fact that it intersects once means what happened? What happened to make it intersect? You're right. What happened? I had 2 X's that were the same. Okay, so what is a function? It is a set of ordered pairs. Is this graph that I just made a set of ordered pairs? Sure, there are an infinite number of ordered pairs that are all connected right there. A set of ordered pairs such that all X values, which is your domain, are paired with only one Y value, which is the range. A set of ordered pairs such that all X values are paired with only one Y value. Okay, so the issue here with this graph was that I had this X value, let's just say it was 1, and I had like an ordered pair 1, 3, and an ordered pair 1, negative 3. Okay, so that 1 being paired with 2 different Y's, that's what made it not a function. And that's how the vertical line test tells us. What do you think a one-to-one function would be? I mean, what does one-to-one mean? Like, for every one of these, there's only one of these? So it would mean that not only does every x pair with only one y, but the opposite is true. Every y is only paired with one x. Okay? So a function which automatically, that word automatically implies each x is paired with only one y, in which each y value is paired with only one x value. So what do you think a test would be for one-to-oneness? Horizontal line test. Okay, so let's take a normal parabola. Okay, is that a function? Yeah, we'd use our vertical line test. Yep, it's a function. Is it one-to-one? It is not, because if I use this horizontal line test, it's intersecting 2 points horizontally, which means that those y values here paired with two different x's. So it's not one-to-one. What would be an example of a graph, just something different here, that would be a function and one-to-one? So vertical line test and a horizontal line test would pass. You think of anything? A line. Yeah, a line that's not vertical. So any kind of line here, let's just do something like that. Okay, so that passes the vertical and the horizontal line test. So this one would be a function that is also one-to-one. Okay. All right, any questions on that? Okay, so here comes the whole brand new stuff. Piecewise function. For piecewise functions, different equations are used for different intervals of the domain. They can be useful for unique types of functions. When we get to some graphs, I'll tell you some situations that might apply to these. But let's just start out with how to graph this. Please, please, please get a pencil with an eraser to start this, because we will definitely be doing some erasing. Okay, so grab a pencil that you can erase. All right, if I look at this, this is crazy. Like, we're going to graph all that. There's so many parts to it, so many pieces to it. Okay, f of x is another name for y. There are 1, 2, 3 pieces to this function. Okay, so the first one is y equals 1. Y equals 1. The second one is y equals 2 plus x. Now, if I'm graphing that, I might just want to be picky and change that around to y equals x plus 2. Y-intercept, slope of 1, okay? And then the last one is y equals 2x. Okay, so I have 1, 2, 3 different pieces to this graph. Okay, but when I graph each piece, I'm going to have to pay attention to these domain restrictions over here and only graph these equations for those values of x. And that's kind of where the tricky part comes in. Okay, so let's just start with this. How would I graph the line y equals 1? What would it look like? What do we call this kind of line straight across? Horizontal. So horizontal line at y equals 1. Okay, so let's just sort of sketch. Y equals 1. Looks like that. Kind of hard to see on top of the line there, but there we go. A little horizontal line. Okay, but I don't want that line for all real numbers. I want that line for x's that are less than or equal to -1. Okay, on a number line, if we shade less than or equal to, we use a closed circle and we shade to the left. right? Okay, so I'm going to go to this graph and figure out where x is -1. Okay, it's right there. That's where x is -1. That's where I want to start my graph. And I want to use a closed dot because it says equal to. And I want to have the graph only to the left of that point. That means that all of this to the right, I'm going to get rid of. So I'm going to totally erase this part of the line. I'm going to start at x equals -1. I'm going to use a closed dot because it said it could equal, and less than is to the left. So that's not really a line at all. That's a ray, isn't it? So it's a piece of a line. So that is the first part of this piecewise function. All right, the second part is the line y equals x plus 2. Let's just graph it, see what it looks like. Then we'll go back and worry about this mess up here. Okay? So if I were graphing this, I would get a 2 on the y-axis, and I have a slope of 1. So think of your rise over run. We're going to go up 1, right 1, up 1, right 1. And connect. And if I left that as is, that's definitely not a function. And I told you that it was a function up here in the direction, so something's off, right? Okay, so I'm going to go to this domain restriction. This means that I want this line only for the points where the x values are between -1 and +2. Okay, so I'm going to go to -1. That's where it's on the line. I'm going to go to +2 on the x-axis, go to the line there. Do you see that those 2 points that I'm pointing the pencil at are where x is -1 on the left and +2 on the right? Between those 2 pencils is the only part I want. I don't want any rest of that line. So I'm actually going to use a closed circle at 2. And look at this. I don't include -1. So technically I'm going to have an open circle there. But that open circle is surrounding a closed circle. So is it an overlap? No. Like this one doesn't include it, this one does, but if you combine that, that point's only part of one of them. So that's closed in because it's part of this one, open technically because of this one. So I'm erasing here, and I'm erasing here. So that line, y equals x plus 2, is only showing up for the x values between -1 and +2. So I took out that little chunk of graph and just kept it. Okay, the last part, y equals 2x. That has a y-intercept of 0 and a slope of 2. So I'm going to rise 2, run 1, rise 2, run 1, etc. And when I connect, it's going to look like that. Okay, clearly not a function as is. But now I have to go back and say, all right, let's check out this domain restriction. I only want it graphed where x's are greater than 2. Okay, so I'm going to go where x is 2, which is right there, and greater than 2 is to the right. Everything over here, I don't want. So I'm going to erase all of this part of the line and just keep this part of the line. And it's going to go on forever because it can be anything greater than 2. Now, is there overlap at this point? No, because this one included 2, but this one didn't. So again, you kind of have a closed circle with a little open circle on top of it, which doesn't include it, so it's all good. There's just one point there. That's a weird looking graph, isn't it? That is called a piecewise. So you are literally taking pieces of different graphs and putting them together. Okay? All right, I know that's weird. You've never graphed one, so who has a question? Are you sure? Okay. All right, let's look over here to the little box. Now I want you to find f of negative 3. Okay, so we did some function notation yesterday. That means sub in negative 3 in the place of x and tell me what y is. Well, I've got 3 different pieces here, but negative 3 only belongs to one of these. So which domain, first, second, or third, does negative 3 belong to? The first, because negative 3 is less than negative 1. So that means I only go to this function and plug in negative 3. Well, how do I plug in negative 3 if there's not an x? I don't. That means y is 1 regardless of what x equals. So what is f of negative 3? 1. There's no place, it doesn't matter what x is, y is 1 anytime that x is less than or equal to negative 1. Okay, if I want to find f of 0, I go back to those 3 domain pieces, figure out which piece 0 belongs to, first, second, or third, the second one, because 0 falls between those 2 numbers. So now I take my 0 and I sub it into 2 plus x. So 2 plus 0 is 2. So f of 0 is 2. Now stop me if you have a question. Okay, f of 2. Go back to your 3 domain. Does 2 belong to the first, second, or third group? Second group, because this one says it can equal 2. This one says greater than 2. 2 is equal to 2, right? So I'm still in this little domain, still subbing into here. So when I sub in 2 plus 2, I get 4. All right, last one, 3.1. Which piece of the domain does 3.1 belong to? The third one. So I plug 3.1 into here. 2 times 3.1 is 6.2. Question. I could have also used the graph for this. So I said, okay, f of negative 3, I would go to 1, 2, 3, go to the y value here, and it's 2. It's 1. If I want f of 0, then I go to where x is 0, go up to the graph, y is 2, so f of 0 is 2. So I could also use the graph. Wouldn't be so easy for 6.2 because that decimal would be hard to approximate. You probably wouldn't approximate 6.2. Okay, any questions on that first one? Alrighty. Oh, I did put a little note here. This one is not discontinuous, but some of our piecewise functions will not be connected. And when they're not connected, they're called discontinuous. So, like, not all of these pieces will actually go together and meet up on all of them. Sometimes they're more choppy looking. Okay, but when they are connected, they're called continuous. So that first one we did was continuous. Okay, example 2. All right, so we have 2 pieces to this one, not 3. G of x is the same thing as y. So I want to graph y equals negative x. Then I want to graph y equals x squared. Okay, so negative x will be a line with a y-intercept of and a slope of, okay, y-intercept 0, slope negative 1. What is the graph of y equals x squared? Hint, it's not a line. A parabola. What does a parabola look like? A U. Okay. So this is our plain old parent graph of a parabola, like its vertex is sitting at the origin, it's opening upward, it's just, nothing fancy happening going on here. All right, so let's graph the line y equals negative x. So graph that on your paper, plot your y-intercept, plot your slope, connect. Make sure it's slanted in the right direction for a negative slope. I don't want the whole line. I just want a part of the line. And the part of the line I want is where the x's are less than 0. Okay, so I go to my graph. This is where x equals 0, right there. Less than, will that be to the left of that point or to the right? To the left. So everything to the left I'm keeping. Everything to the right I'm trashing. Alright, put my little arrow because it will keep going. Now, at this point, do I want an open or closed circle? Open, because it doesn't have the equal to. So let's make that clear. Okay, so that takes care of the first part. Alright, so the second part, that's our plain old parabola. So it would normally be sitting here at the origin, something like that. Okay, but I don't want the whole thing. I want it where x is greater than or equal to 0. Okay, well, this is where x equals 0 on the graph. Greater than is to the right, less than is to the left. I do not want these things to the left. And I do want to keep this to the right. Now, do I include this point? Yes. Now, it happens to meet up in the same point, so really I'm just sort of coloring in that circle there so that that point is included in my whole graph, but it's not overlapped because one of them was technically an open circle. So I have a piece of a line and a piece of a parabola. Those are also connected, so that would be a continuous graph there. So a simple definition of a continuous graph is I could graph it without picking up my pencil. Okay. All right. Do you want to give this part a try over here on your own? Okay. And when I say on your own, please talk to a neighbor or talk to me as I come around. Identify which piece of the domain it goes with and then sub it into that piece. Stop me if you have a question. Rearrange just for the lefties. All right, let's see how we did. What about g of -3? What'd you get? -3? +3, right? Because you sub in the -3 here, but then that negative in front multiplies it or negates it, and it becomes +3. Okay? What about g of 0? Which one of these does it belong to? The second one. Turns out if you subbed it in the wrong one, you'd still get the right answer here, but you got what for your answer? 0. Okay, g of 2. 2 belongs to the second part. What did you get? 4. And 3.1 also belongs to the second part. What did you get there? 9.61. Anybody do that one in their head? I wouldn't have either. All right, any questions on those? All right. Okay, so this next one we're going to do is a disconnected or discontinuous function. A piecewise function that looks like a set of stairs is called a step function. there are continuous breaks or discontinuity in the graph. One such step function is called the greatest integer function. So that is the name of the function. This symbol means greatest integer function. So it's kind of this double leg bracket thing. So this symbol means greatest integer function and is defined as this. Okay, this is a really tricky thing here. Y is the greatest integer less than or equal to x. Or another way of putting that is y is the greatest integer not greater than x. What? That's a little confusing, isn't it? Okay, so let's talk about this. I'm going to draw a number line. I'm going to put 0 here. I'm going to put 1 here. And I'm going to put 0.1, 0.2, 0.5, and 0.8. Those are the numbers that I have in the table over here. And then I have 1, and then I have 1.1, 1.3, 1.6, 1.9, and 2. So all those weird little decimals I'm just getting from the table over here on the left. Okay, so we're going to go old school and we're going to make a table of values that we can plot on the graph to see what this crazy graph is going to look like. Okay, so if I have the number 0 that I'm subbing into greatest integer, the y value will be the greatest integer less than or equal to x. I think we mentioned yesterday that integers are like those numbers that you would use on a graph or a number line. -4, -3, -2, -1, 0, 1, 2, 3, 4. Those are integers. All these decimals that I have here are not integers. So when x is 0, what is the y value that is greater, what is the biggest integer that is less than or equal to 0? Well, if it's less than or equal to 0, it's just 0, right? Okay, so this is going to be 0. 0 is less than or equal to 0, true? Okay? All right, but when I get to 0.1, okay, here I am on the number line at 0.1. What is the biggest integer less than or equal to 0.1? 1 is bigger. 0 is less than or equal to 0.1. Okay, so it's kind of like you're dropping back to the closest integer. So 0 is the biggest integer that is smaller than 0.1. Okay, so this one is 0. All right, 0.2. What integer is the biggest integer less than or equal to 0.2? 0. Okay, so remember, all these decimals are not integers. The only integers that I have on this number line are 0, 1, and 2. What's the biggest one that's less than or equal to 0.2? 0. Okay, 0.5. Here I am at 0.5. What integer is less than or equal to 0.5? 0. Drop back down to 0. 0.8. What integer is less than or equal to 0.8? 0. Okay, but when I get to 1, that is an integer. So what is the biggest integer less than or equal to 1? 1, because it can be equal to it. So that now becomes 1. All right, I move up to 1.1. What is the biggest integer less than or equal to 1.1? 1. So it's like you are, if you're at an integer, the answer is that integer. But if you're at a decimal, you're just dropping back to the closest integer. Okay, so 1.3 maps to 1. 1.6, 1. 1.9, 1. But what happens at 2? Goes to 2. And then everything between 2 and 3 would map to 2 until you get to 3, and then it jumps up to 3. So we're going to plot these. Now, I know it's hard to plot these x's, so we kind of have to use our imagination here. and we're going to see what happens. Okay, 0, 0, easy enough, right there. 0.10, well, I mean, it's right next door, right? 0.20, it's right next door also. 0.50, it's right next door. 0.80, right there. Until I get to 1. And it's not 1, 0, it jumps up to 1, 1. So right here, I'm going to use an open circle to show that I'm going to go right up to 1. But as soon as I get to 1, I jump up to 1. Okay, so all of these decimals between 1 and 2 have a y value of 1. So they're all right here next to each other until I get to 2, and then it jumps up to 2. So I do another open circle there to show that all of these map to 1 until I get here, then I jump up. And then all of these would map here until I get there, then it jumps up. Do you see what's happening? Okay, and it goes indefinitely in both directions. So I also have this little piece of a graph here and a piece of a graph here. And it just continues. It's these little bitty steps. So that's why it's called a step function. Clearly that's discontinuous because it's not connected. I can't graph that without picking up a pencil. Step function is a pretty good name for it, isn't it? It's like little stair steps. Okay, so things that would actually be modeled by this. Way back before you guys were born, cell phone bills were based on a similar setup. So your bill was based on how many minutes you talked. So let's say that between 0 minutes and 1 hour, you would be charged this amount. So like if your minutes were between 0 hours and 1 hour, you had this basic fee. But as soon as you cross that 1 hour threshold, then your charge became higher. And anything between 1 hour and 2 hours was this fee. But 2 hours now goes up to a higher fee, anything between 2 and 3. So something like that nature, might actually be modeled by a step function. Okay? Tax brackets. Maybe you've heard that word tax bracket. It's kind of like a step function. If your earnings are between this amount and this amount, this is the percent tax you pay. But as soon as you get to that next dollar, now you're in this tax bracket. Okay, so maybe not exactly uniformly shaped, but still some sort of a step function. Okay, different brackets of pay. All right, so imagine this at the bottom here. What would 3 greatest integer of x look like? So what if I put a 3 out in front of that? Then all of these y values would be multiplied by 3. These would still be 0. These would become 3. These next ones would become 6, and then 9, etc. What would that change about the graph? It'd be steeper. So it'd be like walking up really steep steps, right? So you'd have a step at 0, then the next step is at 3, and the next step is at 6. So technically, we would call that a vertical stretch, but it's basically making this step steeper. Okay? And isn't putting a 3 on a line changing the slope? Doesn't that make it steeper? Okay, so it's kind of like changing the slope of the graph, the steepness of the graph. Okay, any questions? Please pipe up when you have a question. Something I need to repeat or clarify. Okay, no shyness allowed. Okay, absolute value. We talked about this yesterday. It means distance from 0. What is the absolute value of negative 18? 18, because negative 18 is 18 units from 0. What's the absolute value of 0? 0. Is 0 a positive number? Is it negative? Is it neutral? Yes. Is it even? Is it odd or is it neutral? Even. Can't I distribute 0 pizzas evenly to y'all? Wouldn't that be good right now? Absolute value of negative 5.7. 5.7. Absolute value of pi. Pi. Pi is 3.14-ish. How far is that from 0? 3.14. So pi's absolute value is pi. Okay, we're going to graph the function y equals absolute value of x. Do you know what that looks like? Have you graphed it? Perfect. And then we're going to write it as a piecewise function. Okay, we're going to start old school. We're going to do table of values. Just like we did before with the step function. And I'm going to use the numbers, the integers, from -4 to +4. Okay, so we're going to take each of those x values, sub it into the absolute value, and then that will be our y value. So what is the absolute value of -4? 4. What is the absolute value of -3? How far is -3 from 0? 3. Absolute value of -2? 2. Talk to me. Absolute value of -1? Keep going. Next. And finally, thank you. Okay, now we're going to plot them. So go over to your handy dandy graph here. We're going to plot those points and see what we have. Looks like a line to me. And ruh-roh. What is it? It's not a parabola, right? A parabola would be x squared. It is literally what it looks like. It is the shape of a V. So it's not curved, like it is just a straight edge here and a straight edge here so that it looks like a V. Okay, so here's a really dumb way to remember this. Absolute value looks like a V. So absolute value graph looks like a V. Lock it away. Got it there. Okay, so I'm going to take this V graph, and this, by the way, let's write this down. This is the parent function. Of y equals absolute value of x. So this is the plain old vanilla. Nothing's been done to it. Nothing fancy about it. Like as simple as we can get it, that's what absolute value graph looks like. Okay. So let's write as a piecewise. Now, normally on a piecewise, we will say like f of x, you could do y if you want, f of x is just a little more sophisticated, equals, and then we do this curvy bracket. If you can't do a curvy bracket, do a little square bracket. Now, normally we just put this first bracket, but in that equation editor that I use to write this, it won't let me just use one bracket without the other. So on these, it'll have that right bracket, but we typically leave that off when we write them. So I'm just going to use that left bracket. Okay, how many pieces are there to this graph? 2. All right, so let's pretend, let's totally ignore this right-hand side, okay? Doesn't exist. If you extend that left side and make it a full line, could you write the equation of that line for me? Okay, you would need to know the y-intercept and the slope, right? Figure out the equation of that line for me. Count, rise over, run, literally go from a point to another point to figure out your slope. What's the equation of that line? Did anybody say negative x plus 0? Okay, either way is fine. You can have the plus 0 there. It's not necessary, but it's not wrong either. So I'll go ahead and put it there just for the heck of it so that I have that mx plus b. All right, so everybody's good on how we got that slope? I mean, I'm just literally counting up, left, up, left. So that's a slope of -1. Okay, totally ignore the left-hand side. Look at that right-hand side. Imagine that it continued on. What is the y-intercept? What is the slope? Write the equation. What's the slope of this side? 1. So we have 1x. Y-intercept is 0. Okay, so we can write it either just 1x, x, or x plus 0. Any one of those work. So those are my two equations. Okay, but now we have to go back and figure out, okay, what is this for? X, that is what? Okay, so let's go back over to the left-hand side. What is it? For x, what? What kind of x values do I see here? Less than or equal to 0. What if I said, you're wrong, it's x less than 0? Could we both be right? Yes. But if I say it's just less than, what do I have to use over here? Greater than or equal to. But if you use less than or equal to here, then you have to use greater than. So my point is the equal to goes with one of them. Pick one, doesn't matter, but don't put it with both. Okay? So we'll go with what you said, and I'm going to say less than or equal to 0. But then this one is for x greater than, not equal to 0. Okay? So you can be correct if you put the equal here, but you have to take it away from that one. Okay? All right, any questions on how we got that? Okay, it is not a coincidence that this coefficient is 1 and these slopes are 1 and -1. So if I change the slope, which we're going to do right down here, I'm going to change that slope to 2. This side will have a slope of 2, and this side will have a slope of -2. So we'll just count rise, over, run the same way we would for a line. Okay, so we're going to talk about transformation. So I said this was the parent graph. Anytime we do transformations, we're changing the graph somehow. Okay, so I just told you 2 is going to change the steepness. It's going to be a vertical stretch or change the steepness by basically changing the slope on both sides. What is a -6 going to do to our nice little V up there? Move everything down 6. So it's going to pick up every order pair, slide it down 6. So the point of this V is not at the origin. Where's the point of the V? -6. 1, 2, 3, 4, 5, 6. So let's put a little thing here. Let's put a little note here that this shifts down 6. And that this 2 makes it steeper. Okay, and for the steepness, I'm just going to use a slope of 2 and a slope of -2. So from the point of my V, for the right-hand side, I'm going to go up 2, right 1, up 2, right 1. And for the left-hand side, I need a negative slope, so I will go up 2, left 1, up 2, left 1. And that is my changed or transformed or translated V that went down 6 and is a little bit steeper. Any question on that? Now, if you wanted to, you could do a table of values like we did up here. But if you know those transformation rules, it's quicker to just kind of slide things around and figure out where they'll go. Okay, so let's look at the next one. I have a negative out in front. What is that going to do to the graph? Upside down. Okay, what's a fancy way of saying that? What am I doing? Reflecting over x-axis. There we go. Reflects, we'll get there eventually, over x-axis. Okay, I'm going to jump down to this +4 because we already kind of talked about this. This one moved it down 6. What will this +4 do? Up 4. Because it's plus, it's going to go up 4. All right. What is the +3 going to do? Hint, it's not going up 3. If it was going up 3, that would be a +3. If it was down, it would be a -3 at the end. Right 3? Maybe. Yeah, you have the right translation. It is going to go horizontal. This is the one, I don't know if you remember with parabolas, inside the parentheses was kind of opposite of what you would expect. Plus will actually go left, and minus will go right. Now, the way you can remember that is, what will make that 0 inside there? If x is what? A -3. It's going to move it in a -3 direction. Okay, and if we're talking horizontal, a negative is left. So this is a weird little shift. It will go left 3. If it was a minus, it would go right. Okay, so we take our V. We're going to flip it upside down. So it's not a V, it's like an A. We're going to go left 3 and up 4. Where is the point of my V? -3, +4. Okay, so we're taking that V that was at the origin, and I'm moving it left 3 and up 4. There's the point. And I'm not going upward. I'm going to go down because of that reflection. So what are my two slopes that I'm going to use? -1 and 1. Okay, so I'm going to go down, over, down, over, down, over. There's my positive slope because I went in two negative directions. But if I go down and right, that's a positive and a negative solution, so that's actually my negative slope. Connect them for that nice pretty V. And there we go. Question on it? Alrighty. Next. Okay, we're going to take this one. We're going to do two things. We are going to write it as a piecewise function, but first of all, I'm going to ask you about the domain and the range of this. And then we'll write as a piecewise. Okay, so you guys told me domain is a set of x values. Okay, what kind of x coordinates do I find on this graph? It's not a real easy question, is it? Okay, so I have, I do something to this grass like every day. Y'all will see. Like, they cut the grass, and I swear it feels like every other day. Now he's spraying. It's a constant source of entertainment. Okay, so over here, what kind of x's are these? These are less than or equal to 1. X's. These x's are greater than 1. Okay, well, if I have x's that are less than or equal to 1 and also greater than 1, don't I have everything covered? Like, are there any x's not being used on this graph? Everything has a place. Like, all the negative x's have a point somewhere up here. All these positive x's have a point down here. So my domain is all real numbers. Okay, there are two ways I can write that. Fancy R, or what I prefer is that interval notation, which looks like an ordered pair, but it's not. And we put the smallest number, which in this case is negative infinity, comma, the biggest number, which is infinity. Do you remember that from Algebra 2? Maybe? Okay, so it's always smallest, comma, largest. If we include a number, we use a square bracket. But since these are not actual numbers that we ever get to, we always use parentheses with infinities. Okay, the range is a little trickier. Okay, so what kind of y values do I find here? This part of the graph, the y's start at -1, and they don't ever stop. They go forever up. These y values are all -6. Okay, so this range is going to be kind of weird. For this part here, I'm going to say, what is the smallest y value that I use on this part of the graph? -1. And it's included. That's a closed circle. So I will say bracket -1, comma, remember it's always smallest, comma, biggest. What's the largest y coordinate on this graph? Positive infinity. That means starting in -1, going to positive infinity. Okay, now, union combined with 6. That's a weird one. And I could say like 6 to 6, I guess I could do that. Negative, thank you. See, make those corrections as you see them. And that's it. That one's kind of strange. I could probably just say -1 to infinity, comma, 6. I don't know, that one's really strange since it's just constant right there. Okay, so that's the domain and the range. Now let's write our piecewise function. F of x equals weird little bracket or squared off bracket. Okay, top part. Find an equation of that line for me. Look at your y-intercept, look at your slope, find the equation. Compare with a neighbor. What's your equation of that line? Anybody? -2x plus 1. Do we all agree? All right, I do too. For what x's though? For x is what? Greater than or equal to 1. I like part of that. But greater than 1 is over here. Less than or equal to 1. Perfect. Because the y is -1. But what's the x coordinate here? +1. I know, it's so tricky. So for x's that are less than or equal to 1, so starting here and anything over this way, I want to graph that line. Okay, second part. What's the equation of that line? Think of your y-intercept, think of your slope. Anybody? Y equals -6. If you really want to, you could say 0x minus 6. Because the slope is 0. How steep is that line? It is not steep, it's flat. Here goes Dr. Love. Y equals -6, or 0x minus 6, if that makes you happy. Okay, for what x's? Greater than 1. Do you think it's easier to graph one of these or write it? write it? Who thinks graphing it's easier? Maybe half and half. Okay. All right. So guess what we get to do next? Okay, I've got 2 curveballs in this one. How about we all try to do the first piece, because that's the most straightforward piece of it. Okay, so the first piece of that graph is y equals negative x minus 4. And you're going to graph it only where x is less than negative 3. Let's see if we can get that piece down. The next two both have a little trickiness to them. All right, are we pretty confident with this part? Okay, Charlie, I have some, as soon as we finish this one, I'll bring them back there. Okay, so I'm going to have a y-intercept of negative 4. Let me catch up with y'all. 1, 2, 3, 4. And a slope of negative 1 is going to look like that. Okay, but I only want it where x is less than negative 3. So negative 1, 2, 3. I'm actually starting at that one and going this way. So I'm going to have that right there, nothing down here, and an open circle right there. How's that look? Does it match what you have? So start at negative 4, do your slope of negative 1, that gives you this line, but I want to chop that line off where x is negative 3, which is right there. Stick with this, ditch this. Okay, are we all right on that part? Okay, this next little part's a little tricky. If x is 0, y is 2. Okay, so think about that. Y is 2 when x is 0. Not greater than, not less than, just equals 0. Okay, well that's the same thing as me telling you there's a point 0, 2 on the graph. When x is 0, y is 2. So this point is just a dot on our graph. And I'm not going in either direction. I just have that little point sitting there. Okay, and the only reason that is because is that this is only when x is 0. Not less than 0, not greater than 0, just at the moment when x is 0, y is 2. Okay, then we have this third part. What is the graph of x squared? Parabola. Okay, what did this plus 3 do to our graph? Left 3. What do you think minus 3 inside there is going to do to our graph? Right 3. Okay, it's not going to go down 3 unless there's a minus 3 after the squared part. Okay, so tricky. This is going right 3. Parabola shifting right 3. So that vertex of the parabola is not at the origin. It is over here at 3. 1, 2, 3. And then I've got some kind of parabola that goes like that. Okay, I want that parabola only where x's are greater than or equal to 1. Alright, what if I sub 1 into that? What is 1 minus 3 squared? Negative 2 squared, which is 4. So that means the ordered pair 1, 4 is where I'm chopping off this parabola. So I'm going to go to 1, 1, 2, 3, 4 up here. Didn't do it quite steep enough. That's what that piece of parabola looks like. So I went to where x is 1, and I didn't really know how high to make that point. That's why I plugged it in to figure out that order pair. So 1, 4 is where that parabola is cut. And I stick with everything to the right. Definitely discontinuous, isn't it? All right, who has a question for me? Yes.
Where'd you get the 1 to plug into 1 minus 3?
Okay, because I knew that where I needed to cut off the graph was at 1, and I didn't really know how high that parabola was. So to figure out where that point is, I just plugged 1 in, and I found the y value is 4, so that told me to go to 1, 4, and that's where the parabola will start. Any other questions? Yes?
How do you graph it?
It's not very accurate. I do know that the vertex is here because of that minus 3. Now what I could do if I wanted it pretty accurate, parabolas are symmetric. So I could go, okay, this is 2 points over 4 points up. I could go over 2, up 4, and that's that corresponding point on the other side of the vertex. And so that actually would be a pretty accurate graph right there. Just finding 1, 2, 3 points on it. And again, you can sub them in, or by knowing that shifting right 3, I know that that's where the vertex is. Okay. Any other questions? All right, so that is the end of the notes. Good news, you have almost 20 minutes to work on your homework. Okay, the homework is all sketching. Okay, there are 10. I do not expect you to get 100% of these right. I do expect you to attempt 100% of them. Okay, and like I said, you have 20 minutes right now to work on it. So start with whichever one you want. Don't go in order. Didn't go in order. That's totally up to you. But let's hash out as much of this as we can while you're in here so that you can get some help. Okay? Don't forget your Chromebooks tomorrow so we can do our fun online activity. But we will go over this homework first. I don't think it recorded. There's nothing there. 0 videos. These are old ones that I deleted from last semester.